Hello, everybody. Welcome back to Chemistry with Mr. Edelson yet again. Today, we're going to be starting Unit 2. Now, on Unit 2, we're going to be covering Chapter 11 and 12, so it's a little bit out of chronological order. Chapter 11 and 12 are about the advanced models of the atom. Now, as we go through this, do know that, hold on a second, this is on the wrong slide, so I'm going to stop presenting that. I'm going to present to you a different. Okay. Okay, so now we're on the right thing. Okay, so today we're going to be learning about the advanced model of the atom. Now, if you looked at this chapter yourself, you'd probably be really confused, mainly because there's a lot of high-level stuff in here, but I can really break it down pretty easy for you guys. I would say that a lot of you will like this better in Chapter 4, but some of you may think a little bit differently, just because it depends on what type of learner you are, and I understand that everybody learns a little bit differently. Okay, so first off, Chapter 11 is about atomic theory. It's about the atom, energy levels, orbitals, electron configurations, and periodic table properties. Now, the beautiful thing about periodic table properties is this is just a repeat of the sum of the stuff that we learned in Unit 1. Okay? Now, here are our simplified learning objectives. Now, I didn't put the fancy-dancy learning objectives in here just because I felt like I would have scared you too much, like with big words like electron configurations. So if you can answer all these questions, I can tell you that you're going to have a good time with this chapter, okay? So like, what are waves characterized by? What is the relationship between waves and wavelength and frequency? All that stuff, okay? What is a grounded atom? What is an excited one? All this stuff, okay? Now, I'm going to let you look at that, and then we're going to go on to electromagnetic radiation. Now, have you guys ever thought about when you walk outside in the sun, why does that make you feel warm? Light is just light, right? It just helps you see things. Like, why is it making you feel warm? That means like there's energy being transmitted to you. So a light bulb and a fireplace are the same way. Why are they making you feel warm? That's because energy is being transmitted through light. Okay? This is called electromagnetic radiation. Okay? It exhibits wave-like behavior and it travels through space at the speed of light in a vacuum. Now, if you guys don't remember what a vacuum is a place where there are no particles of matter. It's just completely empty of anything. Okay. Now, electromagnetic radiation is very odd because it moves so fast. It behaves like both a particle and a wave. Now, on the bottom, you'll see wavelength. Waves are characterized by three properties. You have wavelength, you have frequency, and you have speed. Okay? Speed is how fast the wave moves, quite obviously. Frequency is how often the peak of a wave will pass a given point. In the unit of frequency is hertz, also known as 1/seconds. Okay? In other words, waves over seconds is the unit for that. Okay, waves per second. Wavelength is the distance between two peaks of a wave. Okay, so a normal wavelength would be about 500 nanometers, and as you can see in the little right side here, you can kind of figure out a normal wavelength. Now, I do want to draw your attention to something. You guys should notice something about this. This is called the visible light spectrum, okay? The visible light spectrum, there's a little device you guys can use to remember this. Roy G. Biv. Roy G. Biv, red is the weakest, violet is the strongest form of light, okay? Or visible light, that is. Now, why do I say that? Because it's got a shorter wavelength, okay? And when you have a shorter wavelength, that means that you're a stronger wave. Now, some of you may think to yourselves, how does shorter wavelength mean that something is stronger? I'm going to show you two like small waves on a piece of paper. If you saw these two waves, I'm not sure if you can see that. I'm gonna just like bring it closer. So these two wavelengths, which one would be stronger? The one with a lot of waves, or the one that looks like a calm sea? Like which one of these waves would you rather be on in the ocean? That's what you need to ask yourself. So when you see that, you should understand that when you've got a lot of waves together, they are shortening the wavelength and making the wave itself more energetic. Okay, so the weakest color of visible light would be red. The strongest color of visible light would be violet. Okay, the red would have a wavelength of about 800 nanometers. A violet would have one of about 400 nanometers. Okay, and another this isn't important to the class, but it is kind of like a cool thing to think about. So when we talk about visible light, you guys have probably heard of UV rays. UV rays, you guys probably all know, stands for ultraviolet. The reason it's called ultraviolet is because it's stronger than violet. So its wavelength is a little bit shorter than violet. Now, if I think about IR, IR means infrared, which means inferior to red, which means weaker than red. So as you can see, science really has a really obvious naming system for stuff. Okay. Now, this is kind of a repeat of some of the stuff we said. You do not need to know anything about Planck's equation, really. What you'll see is E is equal to H times C divided by lambda. Lambda is a fancy Greek letter. Now, beside each of these variables, I put what they are. So you don't need to know this equation. I'm just going to preface that. You're not going to be using this equation, but it helps describe the behavior of waves. The energy of a wave is equal to H, which is Planck's constant, which is just a number that's the same all the time. When you hear constant, that just means it's a number. It's never going to change. Times C, which is the speed of light. The speed of light is always 3 times 10 to the 8th meters per second. Okay? And then lambda is wavelength for wave in meters. There's also a different for that, which is H times nu, which nu is that Greek letter that looks like a curvy V. It just looks like a V with a curve to it. Okay. Now, like I said, you won't see this again till college. You don't need to know that equation. It's an equation that describes the behavior of waves. Okay. So we have to bring it up, but it's nothing that we're going to make you do. Okay. Now, how do we get that energy from the sun? Well, that's photons. Have you guys ever noticed, like, people always ask me, does fire have a shadow? No, fire does not have a shadow because fire is just photons. But light does not give off its own shadow. Now, shadows are caused when something blocks the light. Now, you might be thinking to yourself, well, what is a photon? Now, when atoms absorb energy up through any means, so it could be electricity. So if you stare at the light in your room right now, okay, that light, like the lights in my room, the electricity is being passed through a metal filament inside that light bulb. That is exciting the atoms inside that filament. Those atoms get excited for a split second, but they don't like being excited, okay? So they have to release that energy that they just received. And the way they release that energy is they give off photons, okay? And when they give off photons, they give off light, and most lights will give off heat. If not all lights will give off heat. That's why when you put your hand next to a light bulb, it feels hot, okay? So like I said, photons are a tiny packet of energy, okay? They behave as both a wave and a particle. Now think about it as you moving your hand really fast in front of your face. Now, put your hand in front of your face and then do the John Cena and then do the da-da-da-da. Right, you do that real fast and it looks like it starts blurring the faster you go. That is kind of how a photon behaves, okay? If I've got a particle and it goes like this really fast, it starts looking like it's a wave, okay? And then after it becomes excited, the energy returns back to its normal stable state called the ground state. Now here's an example of what happens when you become grounded and excited. So this is an electron. Let's just say this is hydrogen right here. This is hydrogen in the ground state. When it becomes excited, it jumps to a larger principal energy level. Now, if you guys don't remember the principal energy levels, Just think of it like the rings on those little atom examples that I gave you. It gets farther out, and the atom doesn't like that because it feels like it's losing stability. Okay. A photon's energy depends on the change of energy between the two states. So only certain types of photons are produced. We're talking about that more on the next slide. By the way, side note, all lights combine to produce white light. When I get to this point every year, people ask me what that means, or what happens when you combine all the lights. When I combine all the lights, I get white, because all the colors together are white. Okay. What color sun produces the hottest light? That would be a blue sun, and we're gonna talk about this. But you should think to yourself, well, the colors of the rainbow. You would say Roy G. Biv. Okay. When I think about Roy G. Biv, you would think that the hottest sun would be violet, and we're gonna go over why that's not the case on the next slide. Okay. And by the way, if you don't track what I was saying there, I increase in energy from red to orange to yellow to green to blue to indigo to violet. So, by the way, if you don't know what Roy G. Biv means, that's what I'm talking about. It's I think it's acronym is the word for it, or mnemonic device to remember the colors of a rainbow or the colors of visible light. And then I just told you the colors of visible light. Okay. Now, hydrogen has certain discrete energy levels. They never emit photons between the colors shown. Now, if you were interested in that, you can look at the book. But this is what that means. Hydrogen is what makes up the sun. Okay, in generally most stars. There are some stars that are composed of helium, but they're way colder. Okay. Now, if I'm dealing with hydrogen, hydrogen does not emit a photon at a wavelength that is violet. That is why there is no violet suns. It does emit a wavelength, however, at a blue wavelength. Okay. Now, what people say is they say, well, if hydrogen can emit a photon at 500 nanometers and can emit a photon at 600 nanometers, I bet it can emit a photon at 550 nanometers. And that's not the case. It can only emit at certain steps. So on the right here, you'll see the little comparison. It's not a ramp. It's more of a flight of steps. So if I'm walking up these steps, I can't stop in like the middle of a step and like put both my feet there because I'd fall right back down to the next step. Okay. I have to either stand on one step or go to the next one. Okay. Now this is a fancy way. The discrete energy levels and quantized energy levels. That's a fancy way of just saying you can't emit like a photon, a wavelength between any 2 points. It's whatever wavelength it emits. Okay. So if I tell you that sodium emits light at a wavelength of 500 nanometers, it's only 500 nanometers. If I tell you it emits a wavelength at 500, 400, it's only 500 and 400. Okay. Now you will not need to memorize anything like that. It's just it's a procedural thing that you need to know. Okay. We do not have many questions on the test about this, so don't get too caught up on this. Okay. I would say maybe 1 or 2 questions out of 30. Now, here's where we get into the juice of the chapter, the meat of the chapter. There have been many models of the atom, and this is the best one yet. Quantum means it is there, but it isn't. So if you guys ever hear someone try to sound really smart, say, I know quantum physics. Quantum physics is really complicated, but at the same time, really simple. So with quantum physics, it's saying it's there, but it isn't. So, for example, how this applies to the atom and why the quantum mechanical model became the name of this model of the atom. It's because we know an electron is there by its effect on the surroundings, but we can't see it. We cannot 100% prove it. Now, why is that the case? The only way we can see electrons is through this thing called an electron microscope. It's a really high-powered microscope, okay? But when you have a really high-powered microscope there, what it does is it shoots like essentially a laser beam inside the atom to see, and that laser beam essentially pushes away all the electrons, okay? but we can see those electrons pushing and pulling on other things in the stuff that we can see. Okay, so that's the where it got its name from. Okay, the quantum mechanical model can still be tweaked or changed. It might even be completely wrong. We don't know for sure. You've probably been taught in the past that atoms orbited a nucleus. Well, guess what? Atoms do not orbit a nucleus. They are completely random. Okay, and we can only make best guesses at where electrons are. Okay. Orbitals. So the wave mechanical model, aka the quantum mechanical model, came up with the idea of orbitals. And this idea says that electrons do not orbit like planets around a sun. Do not be misled by the name orbitals, because that does not mean that they orbit. It is a best guess at where a pair of electrons can be, okay? Or up to a pair of electrons, okay? I'm actually going to put that in there. Most oxygen atoms are, oh, by the way, notice it says there are 2 max, okay? What that means is that no single orbital can hold more than 2 electrons, okay? And then my example of here is most oxygen atoms are in the lower part of Earth's atmosphere. Now, if I ask you for a random given oxygen atom where it was, you can't say for sure that it's in the lower part of Earth's atmosphere, because there's about 10% still up in the upper atmosphere at any given time. That doesn't mean that some can't go down or go back up. It just means that most of the time it's going to be in the lower atmosphere, okay? Just like electrons are going to be more likely to be near the nucleus or in these potential spaces, okay? So an example of this, to help you understand, I can say during the school year, now this, if this is during COVID time, I will tell you that this might be a little bit different. You will either be in your bedroom or at school, because you spend 16 out of 24 hours a day in these 2 places. It's just the best guess, right? Because you probably spend 8 hours of sleep at least, and then you spend 8 hours at school at least, okay? So 16 of your 24 hours a day are in one of those 2 places. So it's just like orbitals. I can say most likely you're in one of those places. And electrons behave like both a wave and a particle. Like I said earlier, I'm not going to go over that again, okay? Now, before we go much farther, I'm going to tell you what an orbital is, because I don't want you to be too focused on that. So the first way I'm going to draw this is it's going to look kind of like our old model of the atom. So let's just say I've got my nucleus. I'm not going to draw my subatomic particles here. This would actually be my first orbital. That is called an s orbital, okay? It's a sphere around the nucleus. So let's just say I'm dealing with hydrogen and I've got 1 electron. I can guess that electron is going to be somewhere inside this orbital, okay? But the thing is, this electron can go anywhere it wants to in any order it wants to. It can go anywhere in there, okay? Sometimes it might even go outside that orbital, okay? I can just say most likely it's going to be in there. Do you need to know the size, the shape of these orbitals? No. Do you need to know the size of these orbitals? Kinda. Now, this is what's called a 1s orbital. As you go down the periodic table, you will increase your principal energy level. So that's a 1s orbital. You see that circle? This would be a 2s orbital. Now, why is that a 2s orbital? Because on average, the electrons will be farther away from the nucleus in the 2s orbital, okay? So you just need to know size in relation to everything else. Now, if you're interested, this is what a p orbital looks like. There are actually 3 p orbitals for every principal energy level, okay? We'll get into this a little bit later in the chapter, but it starts looking like a flower. So it kind of looks like that. It's called a px orbital, py's orbital, and a pz orbital. Do you need to know that? No, you don't. So you don't have to worry too much about that. I'll just give you an idea. So in other words, I would have an electron like right here. I'd have an electron like right there, because that figure 8 is all one orbital. And they might swap places at some given time. They're going to go anywhere they want to in there. Okay, just presenting. So a Pauli exclusion principle, and if orbital actually 2 electrons, they must have spins, one up and one down. It's important in class because we do something that's going to be anymore. Each orbital must have one electron before one is filled. So, in other words, if I'm talking about the px, py, pz orbitals, each of those orbitals would have one electron. Each of them had 2. Okay, because that entire principal energy level has one electron to orbital between the time it's started a little bit, but as we go through, we must have an electron in each orbital before we fill any orbital of a single type on a single principal level. Okay. Hund's rule. Every orbital in the sublevel must be occupied before any are doubly occupied. Okay. Now, think of a movie. Think you're still in a movie theater, and you're so happy because you get to watch a movie by yourself. No one else in the movie theater, right? And 2 minutes before showtime, someone you're like, oh man, just hope I sit right in front of me, right behind me. Notice that he comes to grow, and or she comes to grow, or she sits right next to you. How weird is that? Okay. So the way you need to think about that is everything wants to be spaced out as much as possible before you get punched up next to each other. Okay. So that's the way you think about electrons. Okay. As earlier, you know that with each individual orbital size expands. Now, on the right side here, you will see different types of orbital size, and as you can see, progressively crazier. That would be in this orbital. This would be d orbitals, e orbitals, and then this would be f orbitals up here. Okay. Now, I'll tell you the shapes. People always ask what the shapes are. Show them. Okay. Then I'll give you a bunch of stuff to help you visualize it. Look to the greatest principal, you'll find the number of electrons. Valence electrons. Valence electrons is electrons on the outermost shell of your atom. Okay. Now, when I say look to the greatest principal energy level to find that, when I'm looking for the outermost electrons, I'm going to look for the outermost area of atoms. Okay. So if I was dealing with anything in row 3 or principal energy level 3, that means I would look there to find out how many electrons I have. So if I'm dealing with aluminum, number 13, that is the 3rd element on the 3rd row of the periodic table. So that would tell me that I have 3 valence electrons. Okay. Now, in my helpful resources thing that I sent out to you guys, I do have a game in there called Mahjong Kin that might help you figuring out valence electrons, what we're going to be doing in this chapter, because the next slide is about electron configurations. But this game will definitely help you guys kind of follow along with me, and it actually helps you kind of memorize a lot faster with a lot less stress. Okay. As I said, the valence electrons, the electrons in the outermost principal energy level, they determine the chemical properties. Core electrons are not in the outermost shell. Now, that seems like it's obvious to say, but a lot of people start counting core electrons as part of the valence electrons. So you don't need to do that. Okay. We're about to start doing electron configurations. Just do know that there are some things that are exceptions to normal electron configurations. So that's why I put that on there. Okay. Now, first off, I'm going to show you my. I'm actually going to see if I can. See if I can find an image that might help. Yeah, this image will definitely help you guys. Okay, so you may not know what this is yet, but electron configurations are essentially telling you a seating chart of electrons. It's telling you where all the electrons go for whatever atom you're dealing with. Okay, and there are two types of electron configurations that you can concern yourself with: a stable electron configuration and a normal atomic unstable electron configuration. If you have a stable electron configuration, by definition, you will have the same electron configuration, something in group 18. So group 18 ends in 1s2 or something p6. Okay. Now, you guys really don't know what I'm talking about right now, so I just wanted to show you this to preface it, then we'll come back to it in a little bit. But it's like a seating chart. The first section we go in is 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. Okay, now we're going to go through this slowly but surely. Okay, so I'll stop presenting and I'm going to go over the periodic table. Okay, so first off, what is the electron configuration of H? Okay, well, with H, what I need to do is I need to look at what row is it in. What is the principal energy level that S is in? Well, the principal energy level is 1, so I put a 1 there. Then I ask myself, what is the section of the periodic table it's in? So that first block of two groups, group 1 and 2, those are known as the S block. And by the way, helium in the top right corner is also considered part of the S block. Okay? So right now I'm dealing with 1s. Then I ask myself, is that section full? In other words, is H, did that fill up the section completely? Did it fill up any section completely? The answer is no, because it's the first element on the periodic table. It's only got one electron. So where does that one electron go? Well, it goes in the first seat in the S section. Okay? Now, what's unique about this, imagine you got tickets to a sporting event or a concert. You'd say, well, I'll sit in section 219, row D, seat 19. It's the same concept. The only difference is I'm saying that in every single other seat that was filled up before you. Okay? So this would be the electron configuration of H. Okay? Then I would ask you, well, what's the electron configuration of He? Well, it's still in row 1, also known as principal energy level 1. It's still in section S. But what seat is it in section S? Let's count. Hydrogen's 1, helium's 2. Okay? So that means that this is in seat 2. Now, the S section only has one orbital, which means it can only hold 2 electrons. So now this orbital is full. Every other thing on the periodic table is going to have one S section listed in it. For example, if I do Li, first off, I got to start at the top left and then just read my way down. We can do 1S, and then is 1S full to get to Li? Well, yes, it is, because I've got to go to 2S. So if I look at Li is in group 2. Not group 2, it's in period or principal energy level 2. And then I notice that it's also in the S block still. What's the superscript? Remember, these are superscripts for electron configurations. Okay? Well, it's in the first seat in the S section. Okay? So notice the superscripts here. That tells you the seat in the section. So the electron configuration, Li, is 1s2 and then 2s1. Now, let's say a little bit more challenging. Okay? What if I ask for the stable electron configuration of Li? What I need to do is I need to look at the closest noble gas, Li, in atomic number. Well, Li is atomic number 3. A lot of you might say the closest noble gas is neon, which is atomic number 10, but that's not the case. The closest noble gas to Li is He. So the stable electron configuration of He of Li would be the same as He, which you guys know is 1s2. Now, what does that mean for Li? That means Li is giving away that one electron to some other chemical in a bond. Okay? And then this would be stable Li. So I'm going to put STAB, stable Li. So stable Li. Okay? That's an important distinction between the atomic Li and the stable Li. Now, these two things would kind of look identical, but I'm not going to try to confuse you with that. I'll ask you for stable Li, and it should be identical to He. Okay? Because remember, the whole purpose of the ion is to get to a noble gas electron configuration. Now you kind of understand where I was coming from when I was saying all those fancy words. Okay? Now, going on, and we're going to do a little bit more challenging than that. We're going to add some more orbitals in. Okay? So first off, let's do F. That's fluorine, everybody's favorite element. It's very, very easy to remember. Okay? So first off, we start at the top left corner, then read our way down. 1s2. Now, why do I know it's 1s2 is full? Because fluorine is below. It's the level below it, so it's got to be full up there. Okay. It's on principal energy level 1. Fluorine on principal energy level 2. It's got to be full. Okay. Next, I know that 2s2 is full because F is farther down the list. It keeps going. Okay. So 2s2. Now, I know my 2's kind of look like 6's to you guys, but it's just the way I write them. Sorry. Next, you'll notice if I continue following the principal energy level 2 over to the side, I'll notice that there's something else on the other side of the periodic table. That's called the P block. Okay? So that big block of elements, like group 13 to 18, except for helium, that's the P block. Okay? Have you wondered why the periodic table is organized like that? That's because the electrons behave a little bit differently over there. Okay? There are 3 p orbitals. Can you guess why there are 3 p orbitals? That's because there are 6 elements over there. There are 6 electrons to play over there. And remember, each orbital can only hold 2 electrons. So the S block has 1 orbital. The P block has 3 orbitals. Okay? And so, going on, we're doing F. So I'm still in principal energy level 2, but now I'm going to be in section P. Okay? Back up a little bit. Section P. Okay? Now I ask you, what seat is F in the P block? Let's just count the elements over. B is 1, C is 2, N is 3, O is 4, F is going to be 5. So what is the electron configuration of F? 1s2, 2s2, 2p5. Okay? That is the full electron configuration for F. Now, I'm going to do my last example. It's probably one of the ones that I need to do the most to make sure you don't make mistakes later on. Now, there are 4 sections you need to worry about. there is S, P, D, and F. In this class, we will probably never do an electron configuration with F, so I'm not going to waste your time with it. Okay? But if you want to know, the F block is the lanthanides and the actinides. That's that little subsection that's on the periodic table at the bottom by itself. Okay? So let's do titanium. That's atomic number 22. So Ti. We're going to number all the way down to principal energy level 4, and everything's going to be full. So you should know by now that the P section has 6 electrons in it. The S section has 2 electrons in it. So let's go down and let's do this really fast. 1s2, 2s2, 2p6, 3s2, 3p6. Oh, look, we're done with the 3rd principal energy level. Now we're on the 4th principal energy level. We need to slow down. So first off, titanium is not in the 4s orbital. It's not in the s blocks. So I can fill up the s block. So I'm in a principal energy level 4. I'm in section S, and it's full. Okay? But now I'm into a new section of the periodic table. The transition metals are what's known as the D block. Okay? The D block is special. The reason for that is I go down one from my principal energy level. It's just the way that transition metals behave. Okay? So when I go from 4s, the next step in the chain is going to be 3d. Now that may seem odd, but you need to do it in this order. Okay? You have 3d. Okay? I go from 4s to 3d always. Okay? Now, what seat is Ti in the D section? Well, it's the second element, so it's the second seat. So, what is the electron configuration for Ti? It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Now, side note, if you ever go down to the lanthanides and try for yourself, it actually goes down 2 on the principal energy level. So if I'm in row 6, I would be dealing with 4F. Okay? Now, you don't really need to know that, but just something to think about. Okay? Now, you may be asking yourself, Mr. Charleston, why do they pull that out of their hind end like that? Okay? Have you guys ever wondered why most transition metals are +2? Well, it's because they're only losing 2 valence electrons. And now, if you'll notice, the 4s, if I ask you how many valence electrons I had in this element, I would say 2. Because what I do, hold on, let me get this a little bit closer to you. Okay, what I do is I look at the outermost principal energy level, which would be 4. Okay? So the only 4 is right here. And I've only got 2 electrons in the 4th principal energy level. So that tells me that I'm going to lose those 2 electrons. And the reason transition metals are like that is because they only have 2 valence electrons. So that's why most of them only have a +2 charge. Now, the reason some of them are unique is because of ionization energy and Hund's rule. If you remember Hund's rule, all orbitals must be singly occupied before they're doubly occupied. They're more stable if they're all singly occupied than if all but one are singly occupied. In other words, there's only 1 electron in all the orbitals. You don't need to know that, but I just want to give you some background. I just wanted to, give you some background information on what that was. Now, you may tell yourself, Ms. Charleston, that's getting insane. Why do I have to write all that out? I already know where I'm ending up. So if you're one of those people who looks at where you end up and can do the electric configuration like from there is a shortcut. I do not suggest this shortcut, and you will have to know how to do both ways. However, I'm going to show you how to do it. So what you need to do is you need to look at the last crossed noble gas. Okay? In the case of Ti, we're going to do this one. But the last crossed noble gas will either be helium which will be 1s2. But what I would suggest is never use helium for a shortcut, just because it's not worth messing up your mind on trying to remember this stuff. So what I'll tell you is ignore helium shortcut. Anything below principal energy level 2, principal energy level 2 and below, don't use a shortcut for it, okay? However, once you get down below that, if you see anything with P6, that will be a noble gas, okay? So the last cross noble gas for titanium would be principal energy level 3. So it's going to be 3p6. That describes argon. So if I look up at 3p6, that's argon. So what I do is for Ti, what I would do is I would say, well, Ti is Ar in brackets. So that's like saying I'm starting at Ar now. So I'm starting at 3p6. So it's like I completely marked out all of that. So I can literally just write the last two. I can say 4s2, 3d2. Okay? Now let's just say you don't like this cheating chart method of doing this. Okay? There is another way you can think of doing this. First off, I want you to number a paper from 1 to 7 vertically. You need to practice this because if you try to do it on a test, it's going to be hard for you to come up with this off the top of your head. So 1, 2, 3, 4, 5, 6. Oh, I don't know why I did that. 7. Okay. And then beside your vertical, okay, I want you to put 2 beside the 2 and then go down and number it to 7 again. So 2, 3, 4, 5, 6, 7. And I want you to do the same thing for beside the 3. 3, 4, 5, 6, 7. And then I want you to do the same thing beside the 4. So 4, 5, 6, 7. Now, if you're using this device, I don't suggest it because if you set up the device wrong, you will get the answer wrong. Now, in the first column, everything is S. So S, 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 S. Second column, everything is P, 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 P. In the third column, everything is D. In the fourth column, everything is F. So you'll actually notice that on the periodic table, we actually don't have some of these. So you can actually erase some of them, but this makes the device easier. Now, the reason why this system can still be used this way is because, as I've told you earlier, we don't know if the periodic table is complete. So we can actually predict how electron configurations will go just by using this system, okay? So we actually don't need that corner down there. But I do it there because it makes the little system to write these a lot easier, okay? So first off, this is called the diagonal rule. What you will do is you will draw a diagonal, and it will tell you the order in which things go. So this time, let's do potassium, which is K. That's atomic number 19. So that means the superscript of all my electron configuration has to add up to 19. That's another way you can check yourself. Look at all the superscripts in all of your electron configurations, and it will tell you what it adds up to. If it does not add up to the atomic number of the element you're looking for, you did it wrong, okay? So first off, where do I start? Well, I start at 1s. I draw a diagonal through that, okay? And I'm going to go all the way till I see K. I know that K ends at 4s. It's in principal energy level 4, section S. So I look for 4s. I'm going to end here. So I'm going to keep going until I hit there. And everything else will be full. Then I go through 2s. So I draw a diagonal through 2s. Then this is where it starts getting interesting. I'll draw a diagonal, and I'll hit 2p. Then I hit 3s. Okay? Then I draw another diagonal through 3p. Then 3p hits 4s. So now we're right. Now, just if we follow this along, what this is telling us, I go from 1s to 2s, and I keep following the diagonal. And then I go to 2p. Then I go to 3s. Then I go to 3p. Then I go to 4s. Now, if this just confused you, you don't need to use this method. Okay? It's in either or. I'm just trying to help everybody. Okay? Now, everything that I cross there will be full except for 4s. Okay? What seed is K in the 4s section? Well, it's the first element in the S block, so it's going to be 4s1. So I can just say, well, everything else is full. P is going to be 6, S is going to be 2. So let's go through 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. It can be that fast if you do it this way, okay? Or the other way for that matter. You just kind of have to get used to it, okay? So going back to presenting a screen, hopefully that helped you guys do this, because this is the meat of this chapter. I'm not going to kill this again. We've already went over it so many times. I think I've went over it twice already. Just look at these periodic table trends, review them, and then just know that this will probably be either one of the easiest chapters or one of the hardest chapters for you. It just depends on the way you learn. I will tell you that if you have any questions, feel free to ask me. But this is something that you get very easily with practice. So as you go through, what I would suggest is just sit down, practice, and knock it out. Just keep on doing your own thing. After you practice a couple times, if you still can't get it, I would do like some practice problems in the book. Look like chapter 11 problems, and then look at the solutions manual on the back. And then if you still can't get it, just come talk to me, and then we'll solve it. I think most people make very small mistakes here, so you won't have anything to worry about. So hope you had a good time. This is a pretty, I would say, informative video in terms of all the ways that you can do the electron configurations. I don't think there are many other ways to do it, but feel free to go out and look at some YouTube videos to help you if you didn't get it. Come ask me questions. Hit me up on my email. Have a great day, you guys. See you later.